Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we looked in detail at autotransformer control schemes and their operating modes. Today we turn to a critically important topic: how an autotransformer behaves in emergency conditions. We will examine what happens during a short circuit, how to calculate the equivalent resistance, what overvoltages can occur, and how to ensure the electrical strength of the device. Short circuit behavior. In a conventional transformer, during a short circuit, the voltage is applied across the entire winding. In an autotransformer, it is applied only to part of the winding, which changes the calculation. The effective short circuit resistance in an autotransformer is lower than in a conventional transformer. It is calculated as effective resistance equals nominal resistance multiplied by the benefit factor, where the benefit factor is a dimensionless number showing the winding connection advantage. Nominal resistance is the short circuit resistance of a regular transformer. This lower reactive component requires compensation. The autotransformer design must ensure stability despite the reduced reactance. Example calculation. Consider an autotransformer rated 500 kilovolts to 230 kilovolts with a benefit factor of 0.54. For a conventional transformer, the short circuit resistance is 12%. For the autotransformer, the effective resistance is about 6.5%. To withstand short circuit currents, engineers increase the conductor cross-section, the distance between windings, and the mechanical rigidity of the windings and the tank. Impulse and lightning over voltages. Because the windings are electrically connected, the autotransformer is sensitive to overvoltages. When an impulse is applied, for example from a lightning strike, voltage can rise progressively along the winding length, and part of the wave can transfer to the disconnected side. If the winding layout is not considered carefully, this may cause insulation breakdown. The danger is higher when the load is disconnected or the lines are long with a steep wave front. Protection and insulation reinforcement. To protect against overvoltages, engineers use surge arresters, graded insulation, equalizing windings and shielding, and distributing intercoil insulation according to the impedance law. Example, in an autotransformer rated 220 to 110 to 10 kilovolts, the overvoltage on a disconnected terminal can reach 510 kilovolts, which exceeds the allowable value. Electrical strength. The insulation between windings must be designed to withstand both the operating voltage and the emergency voltage. Special attention must be paid to the regulating winding, which is subject to differential voltage, and the switching equipment, which must withstand sudden voltage spikes. Tank construction and grounding effects. The autotransformer tank affects both magnetic and electrical strength. During a short circuit, part of the leakage current can pass through the tank. This creates additional stress on the mounting and the shielding. Grounding the neutral reduces voltage on the disconnected side and allows the zero-sequence current to be closed. The grounding coefficient is calculated as phase voltage divided by zero-sequence voltage must be less than or equal to 1.4. Practical example: a transformer rated 250 megavolt amperes, 500 to 230 to 35 kilovolts, nominal resistance 12%, benefit factor 0.54, giving an effective resistance of about 6.5%. The calculated short-circuit currents are almost twice the nominal current. For stability, the design includes increased winding thickness, rigid spacers inside the tank, and interturn insulation increased from 10 to 16 millimeters. Analogy. Imagine an autotransformer as a pipe with several valves. When the pressure suddenly spikes, like a short circuit, part of the pipe is directly connected, and another part is bypassed through a narrower path. If that narrow path is not reinforced, it will burst. The same is true for the autotransformer. Reinforcement is needed in the thin wall zone. Practice task. Calculate the effective resistance of an autotransformer when the benefit factor is 0.5 and the nominal resistance is 10%. Determine how the short circuit current will change if the resistance is halved. Suggest design measures for this case. Conclusion. Today we learned how an autotransformer behaves during a short circuit, why calculating the effective resistance is important, and what protection measures against overvoltages are used. In the next video, we will complete the series and explore design optimization, how to find the balance between losses, mass, and transformer economics. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.